And then all the way out to two anchors in a cross. Doesn't move at all, this thing. Moves 20 meters this way and 20 meters that way when the tide sets on. So that's basically the chains picking up. Yeah. It's a flat mooring system. Sure. It's quite rigid. Wow. On the end of each of these legs, the rope is. Well, what you're saying is a couple of meters below surface.
Thank you for providing this opportunity to present the efforts of the G2's Oceanic.
Two videos today. Yeah. She's here.
Good morning, everybody. My guess is that we should start our session. 5 minutes. Please, who is co-chairman today? Where is he? Okay. So.
Good morning, everyone. We will start the second day. Session name is Special Session on Kamchatka Tsunami and South Alaska Landslide Tsunami. I welcome Chair and Co-Chair. Our Chair is Professor Vyacheslav Gusyakov. Dr. Vyacheslav Gusyakov is a Chief Research Fellow for Tsunami Laboratory at Institute of Computational Mathematics and Mathematical Geophysics, Russian Academy of Sciences. He participated in numerous expeditions to investigate tsunami stresses both in Russia and internationally. His work is pivotal in advancing the understanding of tsunami dynamics, risk, and mitigation strategies. He served as chairman of the Tsunami Commission of IUGG. He is also a member of the International Tsunami Society, the American Geophysical Union, and the Seismological Society of America. I welcome you, sir. And our co-chair is Dr. Ashin Ho. Dr. Ashin Ho is a researcher working at Japanese Agency for Marine Earth Science and Technology, Japan. We will begin the presentation, keynote presentations. I will hand over to Vyacheslav.
Thank you very much for presentation. I propose to start our second day, our wonderful meeting. We have 6 scheduled presentations for the morning session and 1 additional short one about the measured at run-up heights of the recent Kamchatka tsunami. So the first presenters, Dr. Igor Medvedev, title is here. Please, this is a keynote presentations, 20 minutes. Floor is yours.
Good morning. My name is Igor Medvedev, and today I want to tell you about the Kamchatka tsunami. Why was one of the greatest tsunamis in the recorded history not catastrophic? Kamchatka situated here, and we are here today. And on 29 July, the megathrust earthquake with a magnitude about 8.8 occurred near the southwestern part of Kamchatka Peninsula. And the location of this earthquake source is similar to the location of the Great Kamchatka Tsunami of 1952. And And here you can see the damage of tsunami in Severokurisk, Pramushir Island. And in the first days after the earthquake, the following questions could be read in the press. Why did such a powerful earthquake generate such a weak tsunami? Why was the damage so minimal? And our study addresses these questions, and we want demonstrating that this tsunami was not weak but powerful. And the first mention of a tsunami in Kamchatka was made by Stepan Krusheninnikov here. And he observed the tsunami on the coast of Kamchatka in 1737. And the magnitude of this tsunami was about 9.0 to 9.3. And the maximum tsunami height was about 30 meters in Awache Gulf. And in 1952, the strongest Kamchatka tsunami occurred. The tsunami has run up height up to 18 meters, and the village of Severokurisk was completely destroyed. Severokurisk is situated here. And from 3,000 to 15,000 people died. And now we tell about Kamchatka tsunami that occurred in this year. And here you can see our research team, and our research team consisted of scientists from different institutions, from Shishov Institute of Oceanology, Russia, Moscow, from Institute of Ocean Science, Canada, from Sakhalin Tsunami Warning Center, Sakhalin, Russia, and from the Severokurisk Hydrometeorological Station, Russia. And the earthquake occurred in the Kuril-Kamchatka Trench zone. It is a subduction zone. And here you can see the moment of the earthquake. The magnitude was about 8.7 and 0.8. The depth of epicenter was about 20 to 35 kilometers. And here you can see the arriving of the tsunami wave to Severokurisk, Promusho Island. And here you can see the damage of this tsunami and Severokurisk too. And we study this tsunami based on tide gauge observations and numerical modeling. And here you can see the map with the location of the Russian tide gauge stations. And stations currently operational are shown in blue here. And stations that were not operational at the time of the tsunami are shown in gray here. And I think that we have in near field zone only one station with the high quality data. It is Semyachik station here, red point. And we analyzed sea level data. And here you can see two sea level records for Petropavlovsk station. Here in Avacha Bay. Avacha Bay is semi-enclosed bay. And for Semyachik station, Semyachik is situated in Kronotsky Bay. It is open part of the Pacific Ocean. And at Semyachik, the height of tsunami was about 117 centimeters above the mean tidal level. And in Petropavlovsk-Kamchatsky, the height of tsunami on tide gauge data was only 4 centimeters. And it is important that tsunami waves arrive to Kamchatka coast at low tide. Here, the maximum tsunami waves arrived at low tide. And here you can see the arriving of tsunami in Vestnik Bay. Vestnik Bay is situated here. And here you can see the arriving. And we contacted with the video's creator and asked him to measure the tsunami run-up height. And this tsunami run-up height here was 18 meters. And we analyzed tide gauge data from different parts of the Pacific Ocean. And we used data from IFC, NOAA, DART stations, and Russian tsunami warning system. And all this 302 tide gauges. And we made tidal analysis, we removing tide, and we made high pass filtering. And then we analyzed this residual sea level data, and the maximum tsunami height was was in Buiroca, Chile. It is 2.57. And in Kahului and on Chile coast here, the tsunami height was 1.5, and in Crescent City and Semyachik here, the height was 1.2 meters. And we made the numerical modeling. We used the long wave tsunami model. We used bathymetry from GAPCO and SRTM database. And for initial condition, we used the finite fault model from UCGS here, but we partly modified slip distribution from this model. And here you can see our slip distribution. And we simulated this tsunami, and here you can see the verification of our results based on the DART station. DART station are black, and model results are red here for different DART station. And we validated our result for few coastal tide gauges. And here you can see the results for Adak station here, for Semyachik station, for Japanese station, Hanasaki and Kushura. But we have the high quality results, but for some station we have not very good result. For example, Petropavlovsk-Kamchatsky or Nikolskaya here. And our simulated time series with the high agreement with the observations in the central part of the Pacific Ocean here, and in the on the USA coast, and for South America too, for coast of the Peru or for Chile. And we made the high resolution numerical modeling for the Severokurisk village, Promoshur Island, and here you can see the distribution of tsunami run-up height for Severokurisk. And here you can see the results. Here you can see the observations of tsunami run-up in Severokurisk in 1952 tsunami. And you can visit our poster on Kamchatka tsunami today in poster session. And we compared the tsunami of 2025 and the great tsunami of 1952. And here you can see the distribution of maximum tsunami height above mean tidal level for current tsunami and for old tsunami. And overall, it is very close, but the tsunami height in 1952 were a little higher. And we digitized old tide gauge records for different stations. For example, Pago Pago. for the tsunami 1952, and we compared time series for few stations, and here you can see the tide gauge records for current tsunami, red line, and for old tsunami, it is blue line, and you can show that these sea level records are very similar, but for the most part of the station, the maximum height and the standard deviation of sea level fluctuations was higher in 1952. And we calculated the ratio between the height of tsunami of 1952 to height of tsunami, maximum height of tsunami of 2025, and the amplification factor is 1.4. And in the conclusion of my report, we will return to the questions from the introduction. And the main result that the lessons of old tsunami, great tsunami Kamchatka, the lessons of this tsunami, old tsunami, were hidden. For example, the main social buildings were constructed in the tsunami safe zone, several tens of meters above mean sea level, and industrial buildings are located in the enclosed bays, such as Avachi Bay, and the tsunami warning service was established after the great tsunami of 1952. That is all. Thank you.
Thank you very much. We have almost 5 minutes for questions, please.
Thank you very much, Igor. Very interesting and a lot of facts. And I, like as a tsunami modeler, I'm just wondering that what really like your observations showed, and if the model could also just be compatible. Like there was no tsunami in Petropavlovsk-Kamchatsky, yeah? And does your model also shows that there is no tsunami? And the second question, also this Semenchuk tide gauge, Semyachik tide gauge showed the first rise of the wave. There was no recedal, recedence. Usually in the near field, in this mechanism, we will await for the well-known recedence, but this was not the case. So does your model also just, can you explain why there was no truth, why there was no recedence?
For this study, we use for all Pacific Ocean linear model, long wave model tsunami, and we have high quality results for that station, but for coastal station, we have different results. For example, Semyachik, we have the good agreement between model and tide gauges. For Petropavlovsk-Kamchatsky, we have not good agreement. And I think that the tide gauge in Petropavlovsk-Kamchatsky works with big problem. I think that small tsunami, maybe 30, maybe 50 centimeters were observed in Avacha Bay. in Petropavlovsk, but and here we see these results in tsunami model, but tide gauge works with problem. And this situation we see for Nikolskaya. The tsunami signal we found in sea level observations, but the amplitude of this signal is very weak. And in the numerical modeling results, we have strong tsunami in Nikolskaya. But in Adak station, the station with high quality data, we have the good agreement between, and we think that Nikolskaya and Petropavlovsk have some problem. And yes, the first wave has a positive and we observed this in our model results and in observations data. But unfortunately, only Semyatchik station in near field have high quality data.
Okay, next question. Okay. I would ask about short questions and short answers. It was so big interest.
Thank you. Thank you. Basically, thank you. Nice presentation. My question is very short. Of course, actually, during this model validation, along with the tide gauge observations, are you able to find what is the role of bathymetry near tide gauge during the simulation of the numerical modeling?
We used gap bathymetry for all Pacific Ocean, but for local gap bathymetry and SRTM data. For local for Sever Kurильsk, we used SRTM data and the bathymetry from navigational maps for this area.
Oh,
yes.
Okay. Thank you.
Only for this area, yes.
Yeah. Thank you.
Lina, please.
Igor, thanks a lot for so much information about Kamchatka tsunami. When you show this comparison between Semyatchik and those records you made and Petropavlovsk, in Petropavlovsk you have high frequency oscillations. So could it be that just the tide gauge couldn't cope with them? It looks like, and at least that's what you get from your simulations. That's what I see here. And another question, I'm just trying to understand why you have such a big difference in neighbor base. And could that be a reason?
In Semyatchik station, we have a sea level pressure sensor, and we measure the water pressure above this sensor. And in Petropavlovsk, this sensor is situated in tide gauge.
Okay.
Old station.
The classical one.
And the tube is very narrow.
Oh, I see.
And I think that this tide gauge was filter the tsunami signal.
Yeah, that's what
And
I thought.
Nikolskaya too, yes.
Yeah, and one just since those are big cities, maybe in addition to that you have observations.
Okay, well,
Observations, some eyewitnesses. So
yes, we
I
have.
will be presented in
Yeah.
the next.
We have video in Petropavlovsk-Kamchatsky, and we can see the tsunami wave on the video in Petropavlovsk-Kamchatsky.
And you can estimate from that, yeah?
Yes,
Yes,
yes.
yes.
In our poster today, we can show these results. Yes.
And one more. The last one, no? Okay, thank you very much.
Thank you.
Thank you very much. Now we have some additional presentation, short one.
Thank you, Dr. Iger. Now I invite Professor Gusego to hand over a memento to Dr. Iger.
Пинегина.
Okay, it is closed actually. Full screen. Full screen.
Yeah, good morning. I'm Ushimo, and I'm the co-chair of this session. First, I sincerely apologize for being late here. I ate too much spicy food yesterday, so during my trip from hotel to here, I have to stop to find a toilet, and which makes cause some delay. I sincerely apologize for that.
Thank you very much. And we have one additional presentation. It's from Kamchatka. It's about measured run-up heights. I was asked to present this because I am not member of reconnaissance team, but I was nearby and can monitor all the stage. It's just 6 slides. To understand what was the main problem. Main problem was very difficult area for making tsunami survey. Kamchatka Peninsula is about 250,000 square kilometers and population only 200,000 concentrated in just in one city. So almost unpopulated. Only two roads. So every field trip, it's very complicated logistic. So that the title of presentation, Tsunami from 8.8 Kamchatka earthquake, July 29th, results of field survey. And the leader of the team, Tatiana Pinegina, Doctor of Science, who used to work in Kamchatka for 30 years as a geologist and paleomorphologist. His area affected tsunami from Petropavlovsk-Kamchatsky, even north of Petropavlovsk-Kamchatsky, up to Paramushir Island. Of course, it was impossible to make any field investigation, but we were lucky to have helicopter flight, the whole day helicopter flight provided by Ministry of Emergency Situation Russia. During this flight was from Petropavlovsk-Kamchatsky until Shumshu and back. There was made several hundreds of stereo photos. And all these measurements were results of careful analysis of these stereo photos and using Arctic Dam high quality data for measuring elevations. What several examples results by means of careful analysis obtained photo, it was possible to restore so-called wet line for most of area where tsunami traces could be visible 2 weeks after the event. It was in most cases, except some steep cliffs the traces of tsunami flooding are very well manifested in the changing color, some remnants, and so on. This is some of small bay, Piratkova Bay, what's 3 other cases. So, and measuring coordinates, making precise measurements of coordinates and heights, Tatiana could retrieve more than 500 elevation sites, more than 500. And the largest was, excuse me, where is my presentations? It disappeared once again. Please help me, please. And this is first time where we demonstrate all set of data from the nearby area. No. This is other presentations. Let's go back to the first one. For the first one. Next. Examples. Okay. In the first presentation, this video was already shown, but I would like to repeat it because it's very unique. It's really filmed the really strong tsunami in semi-closed bay. Так, let me please note. No, sorry. Something wrong. Before the presentation, it worked. Okay.
Волны цунами. Ё-моё.
Roughness of sea. After tsunami. This is unique video of unique event made from altitude about 23 meters, but highest run up in this place was 18 meters. Next about Petropavlovsk-Kamchatsky. Так, let me see, stop, next. It's again a little bit tricky. Next slide. Please. I'm sorry. What's about next slide will be trace of tsunami inside Petropavlovsk. What? Please stop here.
Yeah, I'm
Please
stopping.
Stop here. This is one bay inside of Avachovo. You can see trace of tsunami with amplitude up to 4 meters. So the problem with Petropavlovsk-Kamchatsky tide gauge, because it's installed deeply inside the bay, and second problem is 50 years old, and probably he have severe затухание, damper, yes, severe decay even for tsunami. Here is the final results. Overall distributions with highest mark 33 meters, but on average is of course was much less, between 18 and 20 meters, all along Petropavlovsk-Kamchatsky up to Paramushir Islands. And one more picture, one more feature. Overall geographical distribution. Vesnik Bay is located here. almost near the center of source area. And on the right, you can see rendered list of heights. As I told you, splash was 33, but then 15, 18, 20, 12 meters. So it was strong enough tsunami, all along the nearest coast, at least 3 or even 400 kilometers length. And this result of these measurements will be published soon in Pure and Applied Geophysics. This is bibliographical reference. The team consisted of 16 co-authors. And I hope that this data will be soon placed on global tsunami database as soon as our American colleagues will be able to do this. Okay, thank you very much for your attention.
Thank you very much for your nice talk. Yeah. Are there any questions or comments? Yes, please, Professor Tanioka.
Thank you very much. I want to ask you about the comparison between 2025 and 1952 for those kind of survey. I think a few of them in 1952, but you can compare that tsunami height around the coast.
My second presentation will be entirely devoted comparison of this tsunami with all previous Kamchatka tsunamis. I will try to answer your questions.
Professor Rabinovich, please.
I believe that this presentation is very, very important. I believe that it would be used for many tsunami scientists who are working on numerical modeling. That is why we try to do our best. I'm talking as the editor-in-chief of Pure and Applied Geophysics to publish these results as soon as possible. Just now, this paper is in press, and the publishing house promised that they would do their best to publish this paper maybe in about 10 days. Also, I have a comment related to the comparison of 1952 and this one, and probably you remember that Igor said that the maximum 1952 run-up was 18 meters, but you should take into account that in 1952, there were no real field surveys. So this was just some occasional measurement. So there is no real comparison. I'm pretty sure that if such field survey, detailed field survey would be in 1952, probably we would have something of approximate more than 40 meters in some places.
Thank you very much. And the last question, and yeah, the lady, please.
Okay, thank you very much for your insightful presentation. I have a question about the tsunami arrival time in Velestrin Bay after the earthquake origin time. How many minutes after the earthquake arrived the first wave?
There was some problem. The matter is that on the nearest coast, there was only one tide gauge in Symmetric. Only one time gauge. And as far as I know, the arrival time was very well predicted, plus minus maybe 2 minutes. As for other 300 kilometers, there was no way to measure exactly time of arrival. We can compare it only on the far field tide gauge or 3 nearest dartboards. When people see such a powerful waves, they usually don't pay much attention to time.
Thank you very much. Now let's come to the, maybe we. Okay.
Thank you very much. I'm just adding some information or comment. Yeah, actually, this tsunami also detected in Indonesia. As we in our poster today also write on that the tsunami in Indonesia about 40 centimeter detected in Indonesia. Thank you.
Okay, thank you. So now let's go to the regular presentation given by Professor Gushakov, and the topic is historical Kamchatka tsunamis. Brief overview.
Okay, thank you. In consideration and analysis such unique events like recent Kamchatka tsunami, it's very important to put them on the right place in the row of previous events, and not only in the specific geographical area. That was the main reason to present some historical survey about previous Kamchatka tsunamis. You can see here all historical tsunamis in Pacific area. Kamchatka is small part of Pacific ring, just about 1,000 kilometers out of almost 40,000 kilometers total length. Nevertheless, during last 3 centuries, Kamchatka was a source at least 5 damageable transoceanic tsunami. What they are listed here: 1737, 1441, 1923, of course, 1951, and 2025. And of course, we have to understand why the next major event occurred even this particular area. Actually, nobody expect such a strong earthquake here. On probabilistic tsunami hazard map for the far east coast of Russia, Kamchatka, all eastern Kamchatka coast, of course, colored in red. What on this slide you can see probabilistic estimates for return period 500 years, with probability 90%, more than 6 meters, more than all along eastern coast of Kamchatka. I don't have time to explain deeply seismotectonic, but Kamchatka is located very complicated area, junction of 3 plates, Pacific plates, North American plates, and Okhotsk microplates. And this is, and as a result, it has very complicated pattern of volcanic and seismic activity. Just one fact: all 3 main Kamchatka capes are not part of peninsula. They were driven from very far, from maybe couple of thousand kilometers during last 10 million years by plate movement. So tectonics is very complicated, very complicated. What we have now? We have 42 historical events in total, regional events. Plus, in Kamchatka, there were observed 3 transoceanic tsunamis. Breakdown of 42 events by reason: 37 seismotectonics, 2 volcanics, 1 landslides, with 2 unknown regions. So the main source of threat and nearby subduction earthquake, I mean tsunami threat. And this is maybe most important, my most important features. It's so-called IT diagram, tsunami intensity on Solovyov-Imamura scale for the last 300 years. Tsunami intensity on the Solovyov scales is the best proxy for actual tsunami magnitude. And I will talk briefly about 5 major events. 1737, it's intensity 4, then 1841, intensity 3, then two strong events occurred in 1923 with run-up more than 10 meters. Then, of course, 1952 and the last one. Even before the last megaquake, Kamchatka has the shortest return period between two megaquakes, just 216 years. I mean the distance between 1737 and 52, shortest among all megaquakes in the Pacific area. And right now, just 73 years after, we have another big quake. And this is actually the biggest enigma. Historical catalog starts with the great events, 1737. Of course, we don't have any measurements of this, but second Russian Kamchatka expeditions arrived just 2 weeks after this event. And thanks to presence naturalist Stepan Krasheninnikov, Igor Medvedev in his presentation showed the book, excellent book, and his photo. We have very reliable data and very detailed description of all phenomena, not only tsunami. What kind of facts indicate that Kamchatka 1737 was much stronger event than 52? First of all, duration of strong shaking up to quarter of hour, visible ground waves on the surface, post-seismic changes in coastal relief, then direct indications about run-up heights, 30 fathoms, that is 61 meters on the northern Kurils. Disruption of normal tide in Okhotsk Sea, that never occurs afterwards. And that at that time, all Kamchatka tsunamis were activated. So, judging on all these facts, our expert estimates that this event has magnitude like 7.5. So it was similar to the Chilean earthquake 1960. Next event also was very strong. Sorry, it's skip. 1941. Also very strong. Observed wave heights up to 15 meters. Very long series of aftershocks after 1 year and activation of many Kamchatka volcanoes. Then 20th century, 2 strong events with interval just 1 month between them. Kamchatka earthquake, February 3rd, 1923, about 10 meters at the nearest course, but it gave strong transoceanic tsunami in heights in Hilo about 6 meters. Even there was even 1 indirect fatalities in Hilo due to tsunami. And then less than about 1 month after, in another bay, another earthquake with magnitude only 7, but with maximum run-up up to 20 meters. It was one of the first identified case of so-called tsunami earthquake. Actually, this event was the first one that was studied as by team of geologists from the point of view their paleo tsunami traces, and we could trace sediments of tsunami at the distance up to 1.5 kilometers on the Kamchatka River plain. Okay, and 1952, initial magnitude MS was 7.8, but now we understand, based first of all on tsunami data, it was at least 9.0, at least 9.0. Maximum local run-up 23 meters, but again 6 meters in Oahu, 6 meters in Oahu. Exact number of fatalities was never announced. Only in 90s, some local historians and journalists made expert estimates from 10 to 15,000 people were killed by this tsunami. At that time, there was no tsunami warning system. It was created 5 years later, and since that time, provide the protection. And actually, tsunami warning system made their best job during the last tsunami. Warning was issued exactly in time, just 5 minutes after the events. Some photos from 1952. It was in November, in the morning, 5 o'clock, with very bad weather. That was probably one of the reasons so large number of fatalities. Numerical model of this tsunami. No, finally, 2025 Kamchatka tsunami. You can see the geographical distribution measured run-up height, source location, and on the right, again, very important diagram, how tsunami intensity depend on source magnitude. And both Kamchatka tsunamis fit very well the theoretical line dependence, tsunami intensity on magnitude, but 25 and 52. So no surprise, no features. Tsunami was exactly as we could expect from its MW value. And on this slide, you can I put tsunami travel time for Kamchatka tsunami, and in comparison with similar earthquake occurred 14 years ago in Chile, Maule 2010, and you can see pretty much similarity in propagation time, about 20.5 hours. Distribution of heights, locally it was 20-25 meters, about 1 meter in Hawaii, and from 1 meter on the opposite coast. Both events, as we remember, have the same MW magnitude, 8.8. And the main questions for estimation of the future hazard. When and where will be the next mega quake in this area? In historical records, we have 3 events in Kamchatka, 2 events in Japan, and 1 historical event in Hokkaido. But the big question is, are there possible on the other part of Kuril, Kamchatka seismic zones? Because this kind of mega events give the largest input in tsunami hazard. And another unsolved question is existence so-called Komandorsky Gap. During all instrumental era, it's more than 100 years, we don't have this any really large earthquake. While all the Aleutian Trench was ruptured in several major quakes during the 20th centuries. So I came to conclusion. Through its history, Kamchatka was a source for at least 5 transoceanic tsunamis. Among the subduction megaquakes, it means events with magnitude 9+, all around Pacific Ring, Kamchatka had the shortest return period between megaquakes. And now Kamchatka has the shortest interval, only 73 years, between the major earthquake occurred in the same source area. And all these facts require reconsideration, I would say, reconsideration of the concept, widely accepted concept of seismic cycle and the notion of characteristic earthquakes. That's all. Thank you very much.
Thank you very much for your wonderful talk on historical review of Kamchatka earthquakes. Now, are there any people who can give some comments or questions? Yeah, please, Professor Tanioka.
Thank you very much, Sasha. I'm sorry. Because we have a 1952 and 2025 and 70-30. I forgot. But they have a 1841. You say that that is quite big. Is that big enough to similar to the 1952 or 2025? Because if that is the case,
Even 8.8 is not enough. 8.9. It's strong tsunami, but not damage on the opposite coast places. So just 2 events from Kamchatka was really destructive. 1737 and Kamchatka 1952. The last one was strong enough, but not catastrophic. I mean, in part field.
is there anything the tsunami height in the Shimizu or Paramsil in 1841? Or Paramsil Island?
Can judge how the strength is only secondary relations, like duration of shocks, shaking, duration of shaking, order of hours, 15 minutes. It's strong enough. Activation of tsunami volcanoes. Some data from Hawaii, couple of meters, only this.
4 meter, right? Yeah. How about the tsunami deposit survey in Paramsil?
Yes. describe event, describe the different part of Kamchatka port. You have to understand it. It's very difficult to restore the actual size based on tsunami deposit, based on tsunami deposit. It's, to some extent, it's a reverse problem. It's a reverse problem. Depends not only on the part of the source, but for instance, amount of the sand available to be transported in land. Many factors, many factors. But all these events were well traced, well traced.
Thank you very much. And next question, please.
Vyacheslav, just a short question regarding the gap of the Komandorsky gap. Maybe this is just a consequence of the direction of the Pacific plate because it moves like and can produce only strike slip earthquakes there.
Western part.
Is much more, much more. Expect. That's the worst case.
Thank you very much. And now maybe we still have time for one more short question. If no, yeah, let's thank Professor Gusiak for his excellent talk. And next talk will be given by Professor Zitsev, and which is a virtual talk. And the title is Field Survey and Numerical Simulation of the 2025 Kamchatka Earthquake. Kamchatka Tsunami, sorry, yeah.
That's it.
Good morning, everyone. While they're copying files, I have an announcement to make. Today at 3 o'clock, we have a curtain riser program for Indian International Science Festival. So the problem is we are already running late by half an hour, and we might have to cut the tea time. And we also have a business meeting, which is already, the link has been shared. So I request the participants to maybe one hour, mostly one question. If you have any, otherwise, anyway, all the participants here, you can have this discussion during the tea breaks at the lunch. So please stick to time, and then no questions are only one question. That's my request. Thank you.
Okay. Dear colleague, I would like to thank you for opportunity to present my work remotely. The name of work at slide. My name Andrei Zaitsev. I am from Special Research Bureau, Russian Academy of Science. Okay. Dear colleague, I would like to thank you for opportunity to present my work remotely. The name of work at slide. My name Andrei Zaitsev. I am from Special Research Bureau, Russian Academy of Science. I live in a Sakhalin Island. It's around 1,000 kilometers from epicenter of Kamchatka tsunami, which happened in July of this year. Kuril Island, this is island of my region, north part of Kuril Island, were affected by this tsunami event. So next slide. Oh, okay. I want to say that after 1952 tsunami, Severokurisk city, this is city of Paramoshir, was destroyed, and when city was moved to a safe location zone, and only port zone infrastructure was affected by the tsunami. People were evacuated to higher ground, and from where the port area was clearly visible. Here we can see a video of one of the residents of Severokurisk city make it. And here we can see how what tsunami wave destroyed a fish factory. Our moment. Oh, sorry. Okay. Previous. Okay. Our idea of our survey was to make it in a first day after earthquake. The first survey of tsunami traces in this island was conducted in the area of Severokurisk. We make it our field survey. We use a GPS tracker and conducting field studies to document and preserve data on a tsunami trace which due to a short lifespan and may be lost due to a seasonal storm and coastal processes. The study area, Shumshu Island, this is a close island to Paramoshir, is characterized by extremely increased and completed lack of permanent population. Only sometime one man living in Shumshu Island. This is for staff of a lighthouse. Making prompt documentation of a tsunami trace is critical. Existing estimates of a tsunami height based on the topographic map and are very approximate and require field verification in the future, maybe. The result of a field measurements provided a foundation of a accurately determined tsunami height using high precision geodetic method such as leveling. This will allow for referring to existing model and assessment, increasing their accuracy for the purpose of assessing a regional tsunami risk. One more video was make it with use drone. Here we can see what a tsunami wave around the port area. Here we can observe what a protective wall of a port is almost completely in water. It has height is about 5 meters above sea level. And I would like to note what a tsunami occurs during low tide, approximately 1.4 meter below sea level. Just a moment. Sorry, okay. Okay. Here we provided a detailed survey of a port area of a severe risk. Point 1 has coordinate here. We determined inundation zone by glass flooded by water and garbage lane. And at point 1, by topographic map, tsunami height around 5 meters and distance from the sea level around 450 meters. Point 2 has also almost same height by topographic map around 5 meters and the distance from the sea level 550 meters. Here I would like to note what photo 4.2 was made by residents of severe risk, and we can see what tsunami wave propagate along road and along rivers. Here it's clearly visible. Okay. Okay, point 3 and point 3 coordinate also presented by topographic map around 6 meters and distance to sea level 550 meters. And the water did not reach around 20 meters to the building. Summary picture of a severe risk port zone flooding is presented at the left side of this slide, and here you can see what maximum splash height around of a tsunami is about 10 meters. This is a place shown on a figure. This is a port zone. It has coordinate presented here, and distance to sea level around 260 meters. At this map, we can see port zone inundation line along port zone. Sever-Kurilsk city has located in a safe place, and in our part also here you can see some line of inundation zone of this tsunami event. Next point of our research area, this is a Shumshu Island. Okay, one of our residents make it this video. Here we can see what tsunami flood this coastline. At this point, we can see Here we can see diesel, recrystallization. I would like to note what height of this station, around 6 meters up to sea level.
And conclusions of this report.
Thank you very much, and I hope this paper can be published soon so we can get know more about this paper. And now, because we are run out of time and this is not on-site speech, so we don't have time for question. One, okay, yeah, please.
So this paper was also submitted to pure and applied geophysics. Unfortunately, there were some technical problems with submissions that is why a little delay, but in any case, this paper, I believe the results are quite important and it also will be published soon.
Yeah, hopefully it can be published soon. Yeah. Thank you very much. Now let's come to the next talk given by Dr. John Labrouk. And the title is Kamchatka 2025 underscores GNSS enhanced tsunami early warning development. Yeah. Is Dr. Labrouk online, the JL?
Thank you for providing this opportunity to present the efforts of the G2's Oceania Working Group in developing a G2's capability for Oceania. Before we detail more of those efforts, I would like to highlight the importance of the Kamchatka 2025 earthquake and tsunami to the effort of our working group. This image portrays the model of the Kamchatka tsunami and its intensity. Also shown on this chart as vertical purple rectangles are the observed regions of oceanic surface deformation, resulting basically from a propagating tsunami, as recorded in variations of the total electron content measured from ray paths, along ray paths from a GNSS satellite to a particular ground station. And various satellites are portrayed, therefore indicating various propagation paths through the ionosphere. What this shows is that even for a relatively small tsunami generated by the Kamchatkan earthquake, it is possible to track the propagation of a tsunami. using the TEC technique. Now, G2s relies on two capabilities. The first is the measurement of crustal displacement, which can be incorporated through finite fault models to predict the capability of the likely development of a tsunami. And secondly, through the measurement of total electron content along the ray path, passing from satellite through the ionosphere to individual GNSS receivers. We can track the displacement of the ionosphere from gravity waves generated by acoustic pressure waves from variability of the Earth's surface, both oceans and land. Now, in Kamchatka 2025, it's, as we showed in the previous slide, we observed the TEC gravity waves during much of the tsunami propagation. JPL, through its Guardian system and an upgrade which occurred just days before this Kamchatka 2025 earthquake, demonstrated that using TEC variability, that they could predict they did predict and confirm the generation of a tsunami within 1 hour of initial displacement. This was done in real time and essentially in real time. And also allowed tracking of the tsunami within 45 minutes of landfall at Hawaii. This is a very important development, and it demonstrates that G2s is capable of providing both prediction and tracking of tsunamis. Challenges to G2s are basically that there was only one GNSS station, which was provided to the Guardian system and was not provided to the Central Washington University station, which measures crustal displacement. So the effort thus far has largely been from TEC monitoring, which is the most difficult of them all. But it highlights the importance of international cooperation because there are many more stations in Kamchatka than that one available station. Poor distribution of RT, real-time GNSS station, and poorly supported real-time analysis will limit the potential of G2s. So we really need to strive to develop international cooperation and daily data sharing if we are to develop G2s. Here is an image of the location of GNSS cores stations operating in real time, streaming in real time. In yellow, these stations are basically monuments. They do not provide real-time streaming. So you can see that within the well-developed countries of economies of Australia and New Zealand, we have very high density, but in the Pacific Islands, there are very sparse coverage. The yellows are non-existing stations. Now, The vision which G2's Oceania working group is pursuing was stated within the G2's workshop of 2017 and published by the UN Office for Disaster Risk Reduction in its Global Assessment Report of 2019. It can be accessed at these links. What the working group strives to achieve is a coupling, cost-effective coupling and multitasking of a network of networks for Oceania with selected analysis centers. That network of networks will incorporate national networks, commercial and international networks, etc., and where necessary will create additional networks. Now, as for international cooperation, Oceania is a complex mix of the interests of over 27 nations with territorial interests. And therefore, the success of this initiative will rely upon a robust multinational cooperation. We must achieve this, and if we do, it will be a model for the world to pursue in terms of disaster risk reduction. We are lucky in that we have supporting organizations from the IUGG, certainly, NASA, CNES, Geoscience Australia, Ministry of Lands and National Resources in Tonga, New Zealand, French Polynesia, New Caledonia, etc. And we look forward to more enthusiastic support as time goes on. Now, as far as Tonga's violent tsunami history, it is no stranger to that. On the left, you see one of two major boulders displaced hundreds of feet in the up onto the island of Nuku'alofa in prehistoric times, prior to the arrival of the Tongan peoples over 3,000 years ago. On the right, the more recent Hunga-Tonga tsunami, which resulted in the deaths of 3 Tongans and 2 Peruvians. It was the most violent volcanic eruption ever recorded. To achieve a sustainable network, we must solve this problem where the Pacific Islands have numerous abandoned GNSS monuments and from failed projects. We believe that sustained operation of the Pacific Island G2's networks requires a national commitment to capacity development and data utilization. Through international participation, we hope to provide continued technical support for the nations, the island nations undergoing the development of their G2's networks. The G2's initiative involves initially 2 pilot projects, one in Tonga and the other in Vanuatu. The Tongan pilot project was preceded by the installation of one CORS network by Geoscience Australia. And since this pilot project was initiated, 2 more are planned by by Geoscience Australia. The Tonga Ministry of Land, Central Washington University, and the IUGG have installed 4 of 6 planned core stations. An agreement currently under review by the parties seeks to, 1, develop a control facility at the Ministry of Lands in Nuku'alofa, the development, strengthening of the network capability through power, backup power, and satellite telemetry, and 2 full-time positions for network manager and network engineer with appropriate funding for operations, maintenance, and travel. The Central Washington University and the IUGG will provide funds for the first year costs, and the agreement states that out years will be supported by the Ministry of Lands. This is an illustration of the distribution of the Tonga GNSS network, also known as the TANU network by the Ministry of Lands. Vanuatu project involves also New Caledonia, which is shown in the lower left, and Vanuatu in the upper right. We seek to, this is being led by our French colleagues within the working group, and supported by the IUGG, CANES, the IRD, and the University of Côte d'Azur, who are planning 5 to 10 stations. They may rely upon Central Washington University to provide refurbished TOPCon receivers if funding is not fully available. Thank you. I hope you enjoyed this presentation. I hope you were intrigued by the possibilities, and I hope that you will contribute to this effort. We welcome you aboard. Thank you.
Thank you, John. Are you with us? Can you hear a question?
And I'm ready to answer any questions. Thank you, Slava.
Okay, let me check. Do we have any question about this presentation? One question. Please use the microphone.
Yes. John, thank you for the very informative talk. I wonder, I guess, is this a plot from Lucy that you have on the title slide? My question is, do the purple bars, has anyone looked at the amplitude variation compared to the tsunami model to see if there is a correlation to that can be used in a quantitative way?
Well, the real challenge there is the inversion of the observed variability in the TEC compared to, of course, as you said, the oceanic height variation. Now, it's been considered that an inversion of the ionospheric signal could be accurate to about 20 centimeters, 20% of the actual height. Those would be the error bars. They're pretty substantial, but they're better than nothing other than the tide buoys. So To answer it quickly, no, it has not been done, but this is a challenge that should be undertaken. Thank you.
Thanks.
Thank you, John. And we have one question here in Hyderabad.
Yeah,
Please.
hi, John. It's Yolo Mio from Australian. Thanks for the great talk and also this oceanic initiative that you're undertaking, and also thanks for crediting a lot of effort made by Geoscience Australia, which is a partner with the Bureau of Meteorology. That's where I am. And but I also noted in your presentation there are so many like abandoned or dysfunctional GNS stations in Southwest Pacific. Do you have any tangible plans to revitalize them? And is that what's the challenge? And are they mainly to do with communications or communication channels, or to do with technical capabilities lacking? Or what's the challenge, and what's the plan to maybe bring them into real time? Thank you.
Thank you for your question. I was very happy to credit Geoscience Australia. It's been a major factor in the development of the GNSS networks in the Southern Pacific. And I really hope that they continue to do their excellent efforts. And we intend to, of course, encourage our cooperating nations wherever possible to contribute their data to the APREF system, largely sponsored by Australia. Now, the challenges of establishing networks in the South Pacific are manifold. We, of course, have severe weather, which has been noted to be a problem of maintaining these receivers. Severe storms wrap the surface quite often. Resources, and of course, the installation of these receivers is being reduced in cost considerably as technological development advances. Also, a major issue is the sustainability of the interest in members of the nations that are hosting these stations. It's very important that these nations learn of the value of GNSS, not only in disaster risk reduction, but also in developing their economies. And that's what we're striving to do in Tonga, and we hope to do it in Vanuatu. Now, Vanuatu has many abandoned stations, and so our French colleagues are going to do that conversion. And of course, they will face, and we will face, the challenges of trying to maintain these stations for long periods of time. Thank you.
Thank you very much, John. Thank you very much. Very informative presentation. Okay, we are running much behind of schedule. So I announce the next one delivered by Carlos. Carlos, please. New tools for tsunami monitoring and lessons from, again, Kamchatka. Please, 15 minutes.
Well, good morning. I think you have if you hear your country name every two presentations, probably you believe that are in the right place, in the right symposium. I'm from the Chilean Navy, Chile. So as you can see here, I'm presenting something that we learned and well, that we confirm in the last event in Kamchatka. So probably the title is not correct because there are not new tools. There are new tools requirements or something like that for monitoring. So I'm coming from the Chilean Navy, and we are in charge of the National Tsunami Warning System. So we have some protocols, and those protocols, independently we have a near field or far field event, we have to follow some time, and we have to release our tsunami assessment in 5 minutes after the information of the earthquake. So I'm part of the team that we used a lot of the information that you deliver, and also all the enhancement for numerical models and things like that. It's something that we will use in the future for our assessment and also for disaster risk management. So that is what we got on July 29th. That is the tool, our decision support system, and we identified an event very far away. How far? More than 15,000 kilometers. It is a very long distance. So as I told you, we have the protocol of 5 minutes. So right after the earthquake, we received the first information and we released our first bulletin within those 5 minutes. And then we sent the second bulletin, and the second one was related to arrival time. Those are local times for Chile and also for Easter Island. Isla de Pascua is also part of our territory. So as you can see here, we had 16 hours for Easter Island and 20 hours to Arica, the first continental place where we supposed to get the tsunami waves in Chile. So that is a little bit complicated because also according our protocols, we need to issue a bulletin every hour. And it is the same for our principal tsunami service provider in the Pacific, for PTWC. They also deliver every hour a bulletin. So the question is what to report. That is an important question. And I'm very glad that in the beginning I heard that also we are inviting social science to this group, because it is important to identify what to communicate to the people. Because usually when we have a near field event, we use our tide gauges, we use our networks in order to show, to update tsunami measurements, sea level changes, and things like that. But when you are having a distant event, it is quite difficult because we have some observation gaps. And that is the main message that I would like to deliver to you, because we have a very well-established sea level network and also plenty of dark buoys in the Pacific Basin and also in other areas. So as you can see here, well, most of the coasts are very well covered. And yes, we can see some gaps here. And why? Because there are no islands, only ocean. And if we consider, okay, probably we can plant a buoy or things like that, but I'm not sure if a country or an organization is going to be able to deploy an equipment so distant to a port, because it's quite expensive. So in the real world, what we were facing, things like that. So the distance between Hawaiian Islands to, I forgot the name, but another island from the French Polynesia, around 3,500 kilometers. Then from French Polynesia to Easter Island, 3,800 kilometers. And then from Easter Island to Juan Fernandez Archipelago, more or less than 3,000 kilometers. So in terms of time, it is about 4-5 hours each in terms of distance in the speed of the tsunami. So we are blind in those spots for a very long time, and we have the hourly report. So what can we report ourselves to the national disaster management offices, to the public, to the communities? Because Also, then we run some models. We receive some information from research centers, from PTWC, from other folks, and also the energy is coming to Chile. So we are like we're tsunami makers, but also we receive a lot of tsunamis from Kamchatka, New Zealand, Japan. So all the waves are heading to Chile. So people is able to see this. They feel they are threatened because some waves are arriving, and we are blind in those spots. And it was presented earlier, and the tsunami arrived to Chile. So it wasn't a tale, it was real. So those are some records from our tide gauges, and we were able to see a lot of cities with tsunamis. We didn't see a huge run-ups in our places, but also we got this Boyeruca, more than 2 meters amplitude, tsunami amplitude. So around 4 meters tsunami height. So it's quite impressive since you compare the tsunami amplitudes that were recorded also in Kamchatka. And that was 15,000 kilometers away from the source. And also we got this, some videos that I think are important. I don't feel proud about this video because it was recorded for a person that was in Isla Mocha Island, and the tsunami was arriving. This security camera. But the thing is that we were during the nighttime, and we were reporting to the people, and also we need to maintain the credibility of the system. So it is a very long process. We were monitoring the event for about 30 hours, and we need to report information during those 30 hours. Once we receive the tsunami, when we open our arms and we receive the tsunami waves, and where we are able to monitoring in our networks, it's quite easier in those terms. So it's a little bit long, this video, but I will forward it a little bit. So as you can see here, the difference of the tsunami, and well, I will share later this presentation. So yesterday, Dr. Virfry presented this picture that belongs to Chris Moore, and that is a theoretical layout of the Pacific Basin. So it might be a little bit expensive, cost effective of every single red triangle to put a sensor, because we are maintaining 5 dart buoys, and that is very expensive, to travel 200 miles offshore to do the service and then to return to the port. It's very expensive. You consider that each day of an oceanographic vessel, it's around $20,000. So I think we are in a very good position, because smart cables, I assume that it's going to be a successful project, because I think there is not something about business. It's not money. We will get information that it's going to be useful for the coastal communities. So I think we need to think about how will be our future monitoring. Actually, we have DART, tide gauges, some satellite information as well, as it was presented recently, DAS and smart cables, and other uses of fiber optic cables. So in the past, probably 20, 30 years ago, in the beginning, 100 years ago, when we started with the cables in the ocean, nobody thought about to use that information for other purposes, like sea level monitoring, seismic monitoring as well. But I think that we are running out of money, probably run out of ideas, and I think we have a lot of opportunities of partnerships. Argo buoys. This picture is from yesterday. More than 4,000 Argo buoys floating in the ocean. Actually, that information is well used for conductivity, temperature, depth, also for seabed information, but probably it might be useful for us as well. Also, a lot of sea mammals are monitored by different networks. Seals, sharks, dolphins, whales. Right now, we are using that information only for tracking, to see where are the bird areas, the feeding places as well, but probably in the future we might use it for different purposes like tsunami detection or things like that. Many autonomous vehicles. You know, we have the flight radar. That picture is also from yesterday, flight radar. A lot of planes flying across the oceans, most of them in the coast, most of them in the continents, but also a couple of hundred are flying overseas as well. So maybe today we are seeing those as only a transportation method, but probably in the future we might use that kind of vehicles in order to obtain information. Because we are not going to be able probably to plant in every single red triangle a sensor, but probably we need to do something to think about that. And of course, AI is going to be something that will change our way to monitoring, and we need to use that because all the models that you are presenting here request information for validation. And we are seeing a lot of validations using tide gauges, using dart buoys, but those aren't very specific places, and we need to see abroad because countries like Chile, like the Southeast Pacific by itself, is waiting for 20 hours for a tsunami that is coming to the cities. So this is in Spanish, but the thing is that the criticisms from the social media about the systems. So in 2010, we had the 8.8 Maule event, and it was a big change in our disaster risk reduction. So we don't want to move backwards, and we don't want that the communities think that we are not doing our job. So also we are seeing some other gaps now in national territories, 12 minutes, sorry. And we are adding 2 more stations, one in Diego Ramirez and the other one in Cabo de Hornos. Diego Ramirez is about here. So it's the southernmost island of the American continent. So we will install a tide gauge over there as well. But also, as it was presented yesterday by Ceci, we are doing the feasibility study for smart cable in the fiber optic cable that will connect Antarctica with Chile. For summary, we need to have information for our hourly bulletins, also the sea level measurements, and sea level measurements is the primary information that we provide in those bulletins. Numerical model request for validation, and I think we need to identify another sources of tsunami information, new sensors. We need to think out of our regular sensors that we are using today, because the future is very promising. And partnership, I think, is quite important because we don't have a big pocket. We only have good heart and good ideas. Thank you so much.
Thank you very much, Carlos. You rose very important issue, how to process very far field event. I have a questions to you. What kind of signal, what kind of information did show issue for your coast? It was warning or just watch in case of Kamchatka?
We have our country divided in 21 blocks, and some of them were in the threat level of amplitude around between 1 meter to 3 meters. So it's we call it alert.
Alert.
That is how we call it.
But there was no evacuation.
It was evacuated.
Was evacuated?
Yes.
Okay.
It was.
Please, questions.
Actually, I have a short comment. Gracias for your presentation. And the problems you are talking about are very similar to the problem of the Russian tsunami warning service related to the Chilean tsunamis. And I believe that very few people know that the highest tsunami waves on the coast of Sakhalin Island in the Sea of Okhotsk and in the area of Magadan are related not to the nearby earthquakes in Kamchatka or the Kuril Islands, but the highest tsunami waves were from the Chilean 1960 tsunami, about 2.5 meters on the coast of Sakhalin Island and about 4 meters in the area of Magadan, because there are 6 waves there. So in the tsunami warning service of Russia, it is written like the Chilean, if higher than 8, then, and all the same that you talk just about. So I believe it would be probably quite important to cooperate.
I was talking about partnership, but not that kind of partnership, sir.
One question from online. Please.
Thank you, Slava. Thank you, Carlos. Wonderful talk. I very much like the idea of seal-based monitoring. You mentioned, and I do like the concept of multi-data monitoring, as you know. You mentioned the use of AI as a way perhaps to utilize this sort of multi-data approach to develop the training data sets for the AI problem is a massive amount of work and undertaking. My question is, do you think that it is possible to embed that work within our ICG, or do you think that that work happens best in the research community, the academic community, or do you think it happens elsewhere?
Thank you, Bill, for your question. So probably I have to reply as Vice President of IOC. I'm not sure. But the thing is, well, time is an issue as well. When we think about research and an academia process, probably it might take a little bit longer. So I think that we need is a good relationship between both worlds. ICGs are seeing the operational side, and things like activities like this one and groups like this one are seeing mostly the most scientific area. So I think a good merge between both worlds could be the most feasible and also probably the faster way to do it, because I don't want to see the next giant event without the same layout that we have sensing today, so monitoring today. So I think we are running out of time, and we have very brilliant people, smart groups as well, that probably they can find the solutions very quick. But also then there is another issue, the clearinghouse mechanism and all the issues with data that probably we will get the solution, but then we will have some lawyers in between that will reduce probably the pace in our work. Thank you.
Thank you, Carlos, once again. Okay. And move to the next one. Next one. Так. Online. This is the last one for special session. Okay, please. Your 15 minutes, yours.
Thank you. It's great. So thank you for the introduction, and thank you to the organizer for this very nice event. And also thank you to all the people involved in this work. And special thank you to Carlos. So I think I can give you a couple of minutes back because he covered a lot of very, very important parts. So what I'm working on is really telecommunication and not tsunamis. But we are engaged in this now because we are trying to understand how we maybe can help to fill some of the gaps in terms of global tsunami sensing coverage. And especially what is happening now in the telecommunication sector that you may or may not be aware of is that we're actually changing the global patterns which we are building out submarine cable infrastructure. So the classical corridors that you can see here may mainly there is one over the Atlantic. Maybe you cannot see it over here. There is a main one between the Pacific that have been used for decades, but you also see a lot of new cables popping up, mainly in the South Pacific. We're now looking, for example, at cables going all the way to Chile, coming out, oh well, screw it, down there, and more cables being connected. And this map is now about a week old. So these are cables that will be in the water by the end of 2028. Actually, maybe I can do it. Can you see pointer option, laser pointer? Yay. So you see cables looking here. You see overall a very big build out in the South Pacific. Same in the Indian Ocean. We see new and new routes popping up, looking at connections, for example, between Australia, India, and so on. And the same, of course, goes for the Atlantic. So the question then becomes, can we use this for tsunami detection? And how do we do it? And when it comes to cables, there's really three things we can do. The first one is that we could make some of these into dedicated cable observatories, such as the ones deployed offshore Japan. This is, of course, ideal, but it's very expensive. We had great talks yesterday from Ceci and others about mentioning smart and how we can basically do a hybrid solution where we integrate telecommunication and dedicated sensors together. The first ones are expected 2027, and they are part of the map I showed you last. There's 2 cables located there. The rest of them are non-smart. And the other thing that's been discussed more and more is if we can use fiber sensing, both on existing and future cables. And this is important because both smart cables, the ones that are being deployed now, actually have fiber sensing as part of their solution. And we also see a lot of work coming out of Japan looking at how fiber sensing can complement even the dedicated cable observatories. So it's a very exciting future there. How does it work? Well, if you want to detect a tsunami wave, you need to have something that is sensitive to the tsunami. And in this case, we have a thin fiber on the bottom of the ocean, which is sensitive to pressure, because pressure basically changes the length of the cable, and we can detect this using interferometric sensors. And the main method so far has been called DAS, or distributed acoustic sensing, which is really a fantastic tool. It's about a decade or so, slightly more old. But the limit of this is really that you cannot go very far. You can only go about the first 50 kilometers or so, which means that you cannot really go out to the kind of distance that is covered by the typical dart buoys and the distances we really want in terms of tsunami early warning. But despite this, there are these beautiful figures like this one coming out of Jamstack, showing really amazing recordings. But that raises the question, which is what I'm here trying to tell you today, is this reach limitation fundamental? Meaning, are we battling physics, or is it merely an engineering challenge? Because it's a very important distinction between battling the laws of physics and doing more sophisticated engineering. And in our case, we believe it's not fundamental. And what I'm going to show you are basically experimental data from the Kamchatka earthquake captured on a cable between California and Hawaii. And without spending too much time, because we're a little late on the cable, let's just say it's about 4,400 kilometers long. Most of it, more than 4,200 kilometers, are in deep water, so sub 4,000 meters. And it has about 100 optical repeaters. The important thing and important takeaway is that the first repeater sits about 45 kilometers offshore, meaning that the limitation of any traditional sensing technology is about 45 kilometers. The Kamchatka earthquake, we had a lot of talks about that. Let's skip that one. Here's the important one. This is the DAS data we recorded, illustrating the first repeater. So this is basically as far as the other conventional instruments that sat on the cable could see. And you can, of course, do this on the Hawaii side as well, but it doesn't really change the picture. It's actually slightly shorter there. The important thing is that we believe that, and hopefully now we can show you that this is not the limit of fiber optic sensing. You can go substantially further. So if we look at this a small part in the beginning, we had about 100 meter spatial resolution in our case, but you can really extend this, and it is possible to do, maybe if this comes on the screen, what we call transoceanic distributed fiber optic sensing, meaning that we can maintain the performance of DAS, but now expand to the entire ocean basin. So in this case over here, you basically see 100 meter space sensors all the way from California and Hawaii. And in red up here is the small window I showed you on the last slide. If anyone has good input on how to visualize this in general, that would be great, because it's a lot of data points and it's kind of hard to visualize. Let's, in the interest of time, skip this. The question, of course, becomes, can we detect a tsunami? We can save some time. So here's again, this is the data from NOAA, their nice illustration, and the cable illustrated by the black line, as well as the data recorded on the tide gauges offshore California and Hawaii. In our case, we didn't really have access to any sensors in between, so it's hard to compare all the data, but it does raise the question, is this cable able to provide complementary data? And again, if we think of traditional DAS, even though we and others show that you can record this tsunami on it, it doesn't really change the scope much because there is actually a tidal gauge sitting very, very close to the fibers on both sides. So even if you have DAS, you could just look at the tidal gauge, which means that what we are really interested in here is really offshore data. And you see one such recording here. So this is illustrated by the orange or red dot. It's about 500 kilometers offshore Hawaii, so pushing out in the deep ocean. And what you can see here is the data recorded by our fiber optic sensing system. You, of course, see the very, very strong earthquake in the beginning, but you also see the tsunami popping up after a bit over 5 hours once it hit Hawaii. And this is important because, first of all, it shows that we can have sensitivity down to about 100 microhertz. So the tsunami pops up between 100 microhertz and maybe 50 millihertz or so. But it also shows that this cable is 25 years old. So it's not perfect. It's not as good as a dedicated smart cable would be, or it's clearly not as good as the cable observatory, but it's out there. It's part of the about 600 cables that I showed you on the map before, and it could potentially be a path to rapidly scale the amount of sensors we have. And then looking at fusing the sensors, as Carlos talked about, together with all the other sensors we have. Fiber optic sensing won't be the solution alone, that is very clear, but potentially it could fill some of the gaps, especially when you look at the time scale it takes, because this is something that we can retrofit on the existing cables. So I will be rather quick, but let's start from the California coast and just go through, and we can basically look at the tsunami wave. So here is the close to the coast. Sensitivity is not as great. As we go further out in the ocean, we can see that it pops up, and we will basically step along the cable in increments of 500 kilometers. That's not the limit. We can, of course, do this. We need about a kilometer or so of averaging to find it. But in the interest of time, I think we'll stick to 500 kilometers distance. Here's 2005 kilometers of shore. So this is basically in the middle between California and Hawaii, out in the deep ocean. And as we get closer, we arrive at the figures I showed you before. You can line them up, and you can basically track the arrival of the tsunami in real time. And the total processing latency for each of these data point of the real-time system is sub-second. So it takes less than a second from the fact that the event is hitting the fiber optic cable until it's processed through the entire signal process chain and is outputted somewhere. Again, a little bit more pictures of the tsunami, but I think in interest of time, I'm sure you got the message. So let's wrap this up. The core thing we're trying to tell you here is that fiber optic sensing is pretty powerful. It can detect tsunami waves, but that wasn't known from the past. The difference is that it's not reached limitations as was previously perceived. So we can actually extend this out, and we can do it along the entire length of transoceanic cables. The data here had about 100 meter spatial resolution, which gave us 44,000 measurement points between California and Hawaii. We believe that it's the largest coherent detection array to date, which is a fun way of playing around with words. But the important thing is that it's compatible with all the telecommunication cables out there. So this was one demonstration using a very, very old cables, newer cables, of course, easier. But as we move forward, we can look at the potentially rapid scaling of the fiber optic sensing solution. And again, I just like to highlight, because we like it, the figure below here, which really shows that we can track it. With fiber optic sensing, we get all these measurements points out to a single interrogator. They come out in parallel. So it provides us also with a lot of opportunities to use AI, to use machine learning and more sophisticated signal processing. And I like to end by just saying that in this case, there's actually no added processing to the waveforms. So these are raw waveforms. But we need to remember that in our case, we have a beamforming array with 44,000 measurement points. And both earthquakes and tsunamis are pretty good point sources that arrive from a distance. And we're looking at the far field sensor here. So there's a lot of headroom left in terms of signal processing to really use the fact that we have a massive amount of sensors available to us. Thank you very much for your attention.
Thank you. Any questions? One.
Thank you. It's a very fantastic result, I think. So do you compare with the numerical simulation?
So we're doing that right now, both to numerical simulation and to the DART and the few sensors out there. So what we see from both the numerical simulations as well as combining it with the SWAT satellite that captured the earthquake early on. So we know that it was about a 20 centimeter wave. Or the weakest point where we have good sensitivity, we're looking at about a 15 centimeter amplitude. So we can say that that maps very well. What is the challenge in fiber optic sensing gonna run back quickly. So in general, we have a very good understanding for the sensing methods and how the fiber is changing. But because it's a pressure wave that basically is pushing on the fiber that squeezes it, if you can say like that, that means that there's an uncertainty in terms of the pressure to strain conversion, because it's not, we're measuring strain and we are calibrating it to find pressure. So that means that you would need to calibrate the sensor, just like you would need to calibrate DAS or basically any strain sensor that is measuring pressure. So we seem to have very good sensitivity, and it matches the results from the numerical models pretty well. What is important maybe to add to it, of course, we have a lot of measurement points, and part of the beauty there is because this is a telecommunication that is laid, and the sensitivity varies depending on ocean bottom conditions, we can really pick and choose our measurement points. So we can really work with the high sensitivity areas, which is the data I showed you here. So having a lot of measurement points help with that. But it hope to be out there soon. We're working on it. Maybe give it a month or two, and there should be something online that shows all the comparisons. But unfortunately, I don't have it here.
Okay. Thank you very much again. And we completed our special session. 30 minutes behind of time. Now coffee break.
I have announcement. Thank you, Kuseko and Dr. Roshan. I invite Dr. Yuichiro Tanioka on stage to present mementos to our chair and co-chair. We will break for tea, but please join back within 10 minutes and please bring the tea and snacks inside. You can have here. We have other commitments. Really sorry for the inconvenience. Please help us. Please bring it inside and we can have within 10 minutes. We'll join back. And bring the PPTs. If PPTs are remaining to copy, please bring. Online participants, we will join after 10 minutes.
Okay. We have one more presentation within special session. Presentation not about Kamchatka, but another interesting event about Alaska. Is presenter here? Is here. Okay. 2 minutes. Wait. I will try to get more.
See, I haven't up to date on it. I don't know it's being tsunamis. That's what I know. Yeah. Actually, that goes by action, but by balance. You know more than I do. I don't know more.
Okay. Okay.
Probably I will need an additional microphone.
Next is a special section, Alaska landslide. Professor Alexander B. Rabinovich is the speaker.
Hello? I don't know. Can you hear me? Okay. So I'm presenting this talk about this absolutely incredible event, but this is not my study. So I beg your pardon. This is just a very short overview. Professor Tanioka asked me to tell about this event. Actually, the main study of this event was done by the University of Fairbanks. But unfortunately, you know, because of the situation, nobody could come here, and it was even quite difficult for them to present their lecture online. So, first of all, this is the area of British Columbia and Alaska, and this is the area of lots of landslide events and landslide generated tsunamis. This figure I prepared probably about 15 years ago, and since that time there were several additional events in this area. For example, Tanfjord event, when the wave height was 193 meters, and then it was the Elliott Creek event in British Columbia, in the Strait of Georgia, with wave height of about 100 meters, and then just recently a new event occurred here. So, first of all, when we are talking about how strong, how high can be tsunami waves, we are talking about the famous Lituya Bay event, when a wave height of tsunami run-up was 525 meters. So, what is quite interesting that the last event is quite comparable with this one. Actually, a landslide occurred here in this area. You see this area, and in Juna, you see. Not working. Yeah, but in Juna it was a tsunami record of about 36 centimeters, and after this. No pointer. Okay. Okay, sorry, but I believe that you can see what is here. Actually, I myself worked on several other records from the US NOAA network and also from the Canadian network, but I could not clearly find any other signatures of this tsunami except that one in Juna. Okay. So this is a Google photo of this area, and you see the area of this landslide and this long fjord. So tsunami, this landslide actually occurred at the head of this long fjord. So, and I just will show you a few photos. So you see, I believe, quite clear the area of the landslide. These photos were done by the University of Fairbanks. They made some kind of survey using a plane and some aerial photos. So a few more photos. So this is just the area of this landslide. Slava Gochikov recently worked on the Burea event, and you see there is some kind of similarity, but certainly this event was much stronger. How strong was this event? We can actually estimate from two next figures. So, just a second. Actually, the signal, the seismic signal from this landslide was very clear. You can see records from many seismic stations, and you see just the time difference. And here, a comparison of two events. So left is 2015 Tan Fjord landslide, and the right one is 2025 Tracy Arm event. And you see that the signal of Tracy Arm was probably 3 or 4 times stronger. And if the event Tan Fjord was 193 meters, you can imagine how strong was the last event. Here are just two photos made before the event and after the event, and you can compare. And here is just you can read there is some kind of description of these two photos downloaded from the internet. And finally, what is the most important? So, according to the estimates of the USGS, the wave height of the corresponding tsunami was probably about 470 or even 500 meters. That means that this is the second strongest tsunami ever been recorded during the entire instrumental history. More or less, that is all. Okay.
Thank you very much. Any questions? I have a questions. Did somebody make the field survey on the site?
I believe that there were some very preliminary estimates, but I don't know about any real field survey. What I know is that about using just some kind of air photos of this area, but I'm not sure that I know the entire situation quite well. As I said, the key university is the University of Fairbanks, but instead of writing a couple of papers to Science and Nature, they prefer to keep their work on tsunami zoning.
Okay. Any more question?
I hope that this event really would attract your attention, and probably somebody would work on this event more seriously.
Definitely, it looks like it can be the second largest.
The second largest, yes, this is true.
On the whole
this is the second largest event.
Okay, Sasha, thank you very much. Maybe any questions from yes, please. One question from online.
Oh, this is Young. I just want to point out that actually the survey is going to be led by Pat Nanette and Hick in Alaska. I think they have just recently done the survey for the landslide. So I think they will publish something in the near future. especially there's a special session at the AGU 2025 in December.
Okay, great. Thanks a lot, Young Wei, for your comment. And by the way, I hope that you would participate yourself probably in the study of this event.
Yeah.
Okay, thanks. So we closed special session, and without break, we are moving to another session, advanced technologies. And where is co-chairs? Please come.
Wait. Next section is advanced techniques, real-time inundation modeling, use of high-performance computing, AML, etc. I invite Professor Yuichiro Tanioka on stage to chair the section. Professor Yuichiro Tanioka is a distinguished professor and director of the Institute of Seismology and Volcanology, Hokkaido University, specializing in seismology and tsunami research. He is well known for his pioneering work on tsunami generation mechanisms, including influential studies on tsunami generation by horizontal displacement of the ocean bottom. His research encompasses numerical modeling of tsunamis, fault parameter estimation from historical tsunami events, and the analysis of tsunami propagation and impact on coastal regions. Next, I would like to invite Professor Usama Khatri on stage to co-chair the section. Professor Usama Kadri is an applied mathematician and engineering specializing in fluid dynamics and non-linear phenomena. He is a faculty member in the School of Mathematics at Cardiff University, Wales, UK. His research focuses on acoustic gravity waves, wave propagation, non-linear dynamics, multi-phase flow and related areas with applications in physical oceanography, mathematical physics, and marine sciences. I hand over to our chair and co-chair.
Thank you very much. Our session, the beginning from Professor Shunichi Koshimura as a keynote speech. And as you know, I think already everybody knows him, but I have to introduce him. Dr. Shunichi Koshimura is a deputy director and a professor at the International Research Institute of Disaster Science, Tokyo University. He specialized in disaster science, particularly real-time disaster assessment, coastal engineering, numerical modeling, and remote sensing. Professor Koshimura co-founded RTI-CAST, a technology startup providing real-time tsunami inundation damage forecast, officially licensed by the Japan Meteorological Agency. Okay, Koshimura-san, they have a bit. You speak or video?
I think they will play the video.
Okay. Can you play the video? And you answer the questions, right?
Yes, yes. Thank you. Is there anything wrong?
They are copying your files right
Oh,
now.
okay, okay. If it doesn't work, I can speak. Or maybe I can play the video from here.
Looks like it.
Hello, I'm Shinichi Koshimura from Tohoku University. It's a great honor to make a presentation at ITS. I wish I could join physically, but didn't make it. Today, I would like to share with you our research and practices on TsunamiCast by real-time impact-based tsunami-focused facility. I'm a professor at Tohoku University, Japan, and working as a CTO of Tohoku University-based startup RTICast. We are the unique private-based tsunami-focused provider. We gratefully acknowledge the financial support of the SIP program of Japan and NASA Disaster Program of the United States. What we do is based on the experiences and the lessons we had in the catastrophe in 2011 that caused more than 18,000 fatalities, up to about 3% of the population in the inundation zone. We experienced the severe impact by the tsunami inland penetration. So many activities would be fall behind in the first response, disaster relief, and recovery because of the lack of the information of the tsunami impact. Based on the lessons, what we are really concerned about is the tsunami information for resilience. First, let me go with the standard tsunami warning messages provided by tsunami warning organizations. I think this is a quite general kind of information. We had major tsunami warning, and tsunami advisory based on the rapid estimation of coastal tsunami height with pre-computed tsunami propagation model database. Again, these messages are based on rapid estimation of coastal tsunami height. My point is there is no tsunami inundation forecast information provided. That is what we are doing. What we do, TsunamiCast in Japan, is a fully operational GNSS-based tsunami inundation forecast by running Tohoku University's tsunami inundation code with supercomputing capability. Take a look at the right-hand side. We are using GNSS data of the coastal movement to determine the fault rupture model. Then we are using the fault rupture model as a tsunami source to run the tsunami propagation and inundation simulation. That is on left to acquire the estimation of tsunami inundation. So we are doing this in real time with a supercomputer in Tohoku University. This is TsunamiCast in Japan. The value of TsunamiCast with full capability of the real-time tsunami inundation forecast facility is supporting disaster resilience. That means to reduce losses and recover quickly. TsunamiCast provides information on how extensively tsunami penetrate inland. In other words, where is the safe place? How many people are exposed? How many structures and infrastructures are damaged? How extensive disaster relief activities should be deployed, and how much losses are. I think all of you will agree with this. Those are very critical information for the first responders in the aftermath of the tsunami event occurs. Now, our system is almost fully nationwide in Japan. Our main customers are the Cabinet Office of Japan, the central government, and prefectural governments. We started TsunamiCast in 2018, and they then have been expanding our forecasting area. Currently, under the SIP program, we are collaborating with Yusaku Ota and Yuichiro Tanioka to enhance the TsunamiCast capability with offshore tsunami data assimilation. In Japan, JAMSTEC and NIED is deploying and operating the massive and dense seafloor observation network, SNET, DONET, and NNET. we are developing a hybrid forecast method integrating GNSS-based forecast model and offshore data assimilation. We are testing this method for the case of Nankai Trough earthquake with very unusual offshore slip distribution that will be hardly revealed in GNSS data. The forecast starts immediately by receiving a GNSS-based tsunami source model and then assimilated with the offshore tsunami data. In this test, the simulated tsunami wave field is assimilated at 20 minutes. The forecast data shows a good agreement with the test scenario. Let me show you how fast this simulation is. I'm showing here the performance of TsunamiCast for diverse users using the multi-platforms of the high-performance computing infrastructure. The inundation model is based on the nonlinear shallow water theory with 10-meter grid resolution. These bars are showing the time to complete the forecast for next 6 hours with 10-meter grid resolution. Our supercomputer has the performance to complete the simulation within a couple of minutes, and also using GPU clusters of NVIDIA show the same performance that achieves finishing the computation within 4 to 6 minutes. This means that TsunamiCast capability can be expanded to GPU computing platforms in both the cloud system and on-premises server. This makes it possible to transfer TsunamiCast to the world. Now, let me show you some TsunamiCast products. This is tsunami arrival time for inland penetration. I think this product is very critical for evacuation planning to show which part of the land will be inundated in the expected time of arrival. Next is the inundation depth with the extent of inundation, and users can add their own information or data. This is an example to add critical facilities of vertical evacuation shelters for the prefectural government users. They are concerned about how each of the vertical evacuation facilities will be inundated, how many people are in those buildings. Then we apply the tsunami fragility curves to quantitatively estimate the structural damage and also expose the populations. Those are the standards TsunamiCast product. Now, we expand TsunamiCast capability towards the global real-time impact-based tsunami forecast facility. There are 3 functionalities to be integrated. The first is the rapid determination of tsunami source model. This can be made through the collaboration with the seismic monitoring organizations in the user countries. We propose 2 kinds of urgent computing platforms of cloud computing system and on-premises servers having GPU computing capabilities. We are now working with AWS under the new partnership with Tohoku University. Also, the system can be developed as on-premises GPU servers. The last one is the web-based mapping so that the users can get an easy access to the mapping products. TsunamiCast facility has a great advantage of running tsunami inundation model very quickly. This means it can be used for pre-event risk analysis. One example is generating stochastic inundation maps with thousands of rupture scenarios funded by NASA disaster program. This is the animation of showing how thousands of potential Cascadia rupture scenarios produce diverse tsunami inundation patterns. TsunamiCast facility can produce very advanced stochastic loss estimation data. Through expanding TsunamiCast to the world, we aim to contribute to achieving the UN global agendas of tsunami ready and early warnings for all. Working with the partners to prepare high-resolution bathymetry and topography data, we are providing the forecast products. For tsunami ready, producing the tsunami hazard assessment, tsunami evacuation plan, and emergency response plan. For the early warnings, we are going to produce the tsunami inundation forecast products. supporting dissemination and communication of the warning messages, and emergency response. We propose the real-time impact-based tsunami inundation focus facility. This is a cost-effective solution for promoting cooperation to develop new products and services to accelerate early warnings for all and tsunami ready. I'd like to introduce one comment from Professor Karnawati, the head of BMKG Indonesia. She was also emphasizing the importance of endorsing private sectors to accelerate the achievement of early warnings for all. Besides, we believe that this can contribute to the Sendai frameworks of priority for action, especially on investing in disaster risk reduction for resilience to fill the gap between the science and practice of tsunami inundation forecast. Thank you for your kind attention.
Thank you. Good talk. Any questions? Yeah.
Thank you, Professor Koshimura, for this very inspiring and impressive talk. I'm Andrei Babik from GFZ Potsdam, and my question is about the setting for Japan, like that you use GNSS to assess the source model, and you don't basically go for seismic, but just use GNSS. And I'm very happy to hear it, because we at GFZ, we always promoted GNSS for tsunami early warning. But my question is that like a trench in Japan is pretty far away from the shore. Like, so the earthquakes which could be close to the trench, like 7.5, they will probably produce very small displacements on land. And my question is, have you tried to estimate what would be the minimum seismic magnitude which you would see with the GNSS array? And because at some moment the signal would be not visible inside the noise. So have you estimated this minimum magnitude which could be recognized?
Thank you for your question. So actually what we're using is the source model provided by GSI. So they call that product as Regard. And also we are using the algorithm of the RAPID, which was developed by Ota-san of Tokyo University, using the GNSS data. And then our focus are having two kinds of functionality to run the simulation using the different source model. One is using the early earthquake warning, assuming the simple rectangular form. And then the other is the one use the GNS-based tsunami source model. So your thought is right. I think your thought is right. If you have the small earthquake, and then we have the difficulty to get the data from the GNSS station. So in that case, we're going to use only simply the early warnings, earthquake early warning based fault model. And then if you have the larger earthquake, like the magnitude larger than the magnitude 7.5 or something like that, we are using the GNSS-based source model. And on the other hand, we are also recognizing the problem of the GNSS data for the source model determination. So that is the reason why we are working with Tanioka-san to integrate with the offshore sensor data, making that possible to generate the data simulation. So by integrating the GNS-based solution, GNS-based source model, data simulation, I think that is the best configuration using the observation data for the better forecast.
Thank you very much. Okay, let's move to the next speaker.
I think Bill is raising.
Okay.
It's okay. Thank you. Koshimura-san, thank you for the talk. I'm happy to ask you my question offline and continue our previous conversation.
I think we can meet in February. I will planning to visit in New Zealand.
Wonderful. Thank you.
Thank you.
They are using his system to the New Zealand. Okay, let's move on to the next speaker. And next is Dr. Finn Labhart, and toward a new global model for rapid tsunami post-assessment on population exposure.
In the same realm of the form, but it's rather on post-assessment of population exposure than early warning. The background for this talk is that we need to have a rapid assessment of the impact right after the tsunami event, and this is simply to assist second and first responders, etc. I'll get back to that. The methods we will use are amplification factors, human lookup tables on a global scale, and we are also going to show some testing of this. And finally, I'll give an outlook of how this works and who the client and the operators are. Why are we doing this? It's a need for the ERCC, the Emergency Response Coordination Center in EU, to rapidly, after all types of disasters globally across perils, to have a quick estimate of the impact of the event right after it has happened. And the organization tasked to do that is the Aristotle Network in Europe, which consists of several early warning providers across several perils. Tsunami is one of them. And right now it operates on a quite simple basis using the Tsunami height tool for homogeneous rupture to simulate the offshore heights. And we want to take this further to estimate some kind of measure of how severe the run-up heights can be and how many people that could potentially be affected. And this needs to be issued to ERCC within 3 hours. So this service really needs to run within less than an hour or potentially just a few tenths of minutes, which is the aim of this service. The technical background is simply that we had done some similar analysis before for risk analysis, the global assessment report. And the idea was to use the methodology for this to rapidly assess the exposure. And this combines 4 different things: amplification factor methods to rapidly estimate the inundation heights along the shorelines, to snap these heights on the shorelines and project them, and then to integrate and extrapolate the inundation over land and integrate the exposure of populations. And we take into account here that the global assessment report was done in 2015, whereas the data, open source data, has improved a lot since then, particularly on the topography side, where removal of artificial forest buildings, etc., is improving the accuracy. So we have to really use quite approximate methods. This is a global service that's supposed to operate within few minutes globally. This should then could link in principle to any type of simulation service that provides time series outputs at points near the shore. In this case, it's Tsunami High Sea, but it can also operate with other types of services and probabilistic services in principle. A few words about the global amplification factors. They will develop 15 years from now for the global risk assessment. They estimate the coastal maximum inundation heights simply by lookup tables. They will run many linear shallow water models, and we create through simplified profiles, such as the one you see on the top here, the ratio between the offshore height at a given depth and the amplified height, which approximates the inundation height. And the lookup table takes into account the wave polarity and the period of the waves, so meaning that shorter period waves amplify more than long period waves. Also, these lookup tables are available through the GeoInquire project, through the link I provide here. This is also, and finally, it's important to say also these are tested. So we have compared the amplification factors towards several sites, something like 8 sites in the Mediterranean, where we run high resolution nonlinear shallow water models. We test statistically how these factors behave, and then we provide uncertainty curves for the distribution of the heights between the inundation models and also correct for the average biases from the AMP factors, so we can correct them towards better models. So these will then have larger uncertainties than high resolution models. The procedure in Aristotle is then to take these factors, extract the time series heights, such as you see exemplified for Sulawesi here. We can take the time series, we can extract the polarity and the wave periods, and we can estimate simply through looking up the factors when we have the wave periods and the polarity, how much these time series point amplitudes will amplify to an MIH. And then we will do the bias correction and uncertainty in addition to that. And finally, we will move the point values to land, so we have these projected on land, so we can prepare for the inundation mapping. The next step is then to use a very crude method, honestly, for estimating how far inland they go. This is actually a figure that has been employed, a simplified way for New Zealand before, where we do so-called a bathtub approach, but we do a linear friction reduction of the height. And here we can use 3 meters height reduction per kilometer inland. We can also use 5 meters and run several of these as a sensitivity. And then when we do that, we can estimate also beforehand globally on open source topography how these heights would look like. And we can make several layers of them with typically like 0.5 meter resolution, and we step upwards, so we can simply very quickly look up when we have the MIH on the shoreline how far the inundated areas will go, and we will have these stored in advance. So the procedure here is to make a global set of amplification factor for global points. And we have recently done this also for the global tsunami hazard model, which we are presently working on. So we are working with the same data set here, and we combine this with the high sea simulations in the area of interest. And then we take, for each of them, we distribute a set of polygons across the shore, and we predefine the areas that we are looking up the exposure data sets for. For the population data set, we use the global human settlement layer, and for the topography, we use an open data set called the TESSA-DEM. Okay, so putting it all together, we are first getting this input from Aristotle, which is a uniform slip Okada source combined with time series outputs. We then extract the wave periods and polarities, looking up the amplification factors, and we estimate the uncertainty. And then we take these for different uncertainties, extrapolate on land, and we integrate the exposure for the areas that are flooded. We are trying to test this for a few events, most carefully for Tohoku, a little bit less in depth for Indian Ocean tsunami, and we also have some very brief comparisons for Maule and Noto events so far. For Tohoku, we tried to calculate the inundation for different types of uncertainty measures that could either be the median value of the distribution of the inundation heights or the mean value, which is slightly higher because these are skewed uncertainty distributions. This gives us first inundation heights that compare reasonably well, I would say, given the very approximate methods we are using compared to the observed heights. And we see that we in certain areas overestimate, but also underestimate. But there are also quite large spread locally in the inundation heights. And these are some lookup on how this may look when we overlay the inundated areas with the topography. We see that in these cases, we have areas that are relatively well topography controlled, of course. So the comparison in, for instance, here in Ikusentaka might look quite good, but of course we also have steep topographies. On the other hand, we have to also recall the very approximate methods we are using here. With this, we also estimated the differences, and when we are using different types of uncertainty measures, first of all, the median value, we get a quite good estimate of the exposure, which is, if we compare to the police report, which says that there are about 1.1 million doors exposed and 2.2 persons per household, that will give us something like 2.4 million people exposed. And this is actually what we are getting with the median value in this case, approximately. For the mean value and the 84th percentile, we get quite large overestimations. Please consider that this is used for the responders to get a rough number of the exposed estimates right after the event has occurred. It doesn't have to be accurate, but it has to be quite ballpark to tell them if this is really serious or if it's something that can be less serious in terms of sending people to emergency response. For the Indian Ocean tsunami, our estimates were a little poorer, I would say. We got larger spread in the inundation heights. This also has partly to do with the source that we are employing, which is the Fuji source from 2021, and we had some quite low amplified heights offshore Sri Lanka and India, but otherwise, as you see here, for Banda Aceh, the inundation maps are reasonably well covered. And also the exposed estimates are okay. But we get some underestimation for Myanmar and also some underestimation for Sri Lanka and India. Some of these offsets, as said, this is due to the earthquake source we applied. For Maule, here we see the inundated heights compared to the observational field survey, which gives something in the ballpark of the estimates, but with a quite large uncertainty band. As you see here, the median value is in blue, and the 84th percentile is in orange. Similarly, we got also orders of magnitude correct inundation estimates for the Noto event. So to the next step, the service is ready. It's ready to go. It's implemented. It's something that is run by our Aristotle operators in Europe. And it's launched automatically by a Rabbit MQ service. It triggers automatic reports for the inundation and exposure for different segments of the shoreline and nationwide. And it also gives different percentile values. We will probably trim this down very much to either median values or mean and keep the detailed information in the backhand, because the operators needs quite simple numbers to work on, and we are still working on how to make these reports. There are obviously, this is the first time we do this, and there are obviously many improvement points. The amplification factors have very large uncertainties that you have seen, and giving a percentile would give you quite different estimates. So we will probably work on reducing these and improving the amplification factor methods, and also try to then revise the uncertainty measures. Also, we have seen quite an acceleration in the improvement of the open source data sets, and probably the TESA-DEM, which we are using right now, is not the best. We might go to others and then also improve the coverage of the inundation. And with that, I'll thank you for your attention.
Do you have any question, comment?
Yeah, thank you for this very informative presentation. I wonder if you have any intention of taking this forward at some point to the next stage where operationally you can make use of that for optimizing evacuation as well.
I'm not sure if it's really suited for that. I think the last presentation where you use high resolution inundation maps or at least some local information would be necessary. Consider this is using open source data sets, and And to use it for a local assessment, I would probably be careful. It is more to give an integral estimate, and because it's global, it has to be, at least at this stage, right, relatively crude. So I would probably think it needs some kind of finer, in-depth local information to be used to do.
So right now it's not built in a way that the local information can be replaced.
Well, in principle, it could if you have local topography data sets
and roadmaps and
yes.
other factors.
Yeah, but we haven't that right now. No.
Thank you.
May I have a question too?
Yes.
Because you have a distance and the height is a parameter, right? So you have a topography on it. So
Yes.
they might the distance and height might be, I mean, different lines. So how do you make it?
It's simply a geometric method. So you do an estimate from the shoreline based on this type of bathtub approach to simply estimate the line of sight from the shoreline point. That's it. Sorry, I'm just trying.
So that like a very, I mean.
So you see it here. It's for one of these colors. All of them have the same height, and then you know the shoreline length, so you can take the yeah.
But that length and the height might be a different point.
Yeah, it intersects the height.
Yeah. Oh, I see.
Yeah. It intersects the height, so you see it's variable, right? Yeah.
Okay.
Yes.
Thank you.
Oh, good point.
Sure.
Finn, I didn't get to the point. Like you show that you have these statistics uncertainties, like mean value, but you have only one source, like seismic source, which comes from Aristotle. Where does uncertainty come from?
Uncertainty comes from the lack of precision of the inundation method only. I mean, but it could be combined with the probabilistic forecasting. But in this case, it's a deterministic source only. So you have to convolve it if you want to do that. I don't think it's very difficult. I think it's possible way forward actually.
Okay, thank you very much. Next one will be the video. Dr. Gui Fu, PIM tsunami. A tsunami hazard amplification model, considering site factors and applying physics-informed machine learning. Are you here?
Hello everyone, I'm Gui Hu. Thank you for arranging the online presentation for me. Thank you very much. Before presentation, I want to say much of the work has not been published, so please don't take pictures. Thank you very much. And today I want to share the first stage of my Mercury postdoc fellowship project, and it's about how the tsunamigenic factors will influence the tsunami size and tsunami behavior in the deep ocean and along the coastline. In today's presentation, I will use the 2025 Kamchatka earthquake and tsunami as an example. For those who don't know me, I'm Gui Hu, currently a Mercury postdoc fellow in the University of Bath, UK. I research earthquake and tsunami. I research earthquake source mechanism, tsunami hydrodynamics, and tsunami hazard impact. I mainly adopted joining version of seismic data, GPS data, and satellite data, and tsunami modeling and analysis to conduct my research. If you want to know more about me, please see the additional information at the bottom. And in the following slide, I will first introduce my Mercury postdoc and fellowship program, and then use the 2025 Kamchatka earthquake and tsunami event as an example to explain my Mercury postdoc project. For a given earthquake, tsunami size can vary by 2 orders of magnitude. Many tsunamigenic factors can influence tsunami size, including plate age, plate velocity, plate fraction, subduction geometry, shallow deep angle fault, and the horizontal seafloor motion, and kinematic rupture, and sediment thickness. However, with current techniques and dataset, some of those factors cannot be quantitative analyzed, but some can. In my project, I focus on how subsurface structure, subduction geometry, shallow fault, horizontal seafloor motion, and co-seismic earthquake rupture, how those factors influence the tsunami behavior and the tsunami size. Currently, I've completed the collection of various global datasets along with data processing and official website development. Welcome to follow our official website and check for updates anytime. Next, I will conduct tsunami modeling and apply machine learning to establish the quantitative relationship between tsunami-genic factors and the tsunami behavior. The above is my brief introduction to my Marie Curie postdoc fellowship project. To quantify the effect of the tsunamigenic factor on tsunami, we use the 2025 Kamchatka earthquake tsunami event as an example. In this event, several tsunamigenic factors are discussed, including the uniform Earth model, layered Earth model, horizontal seafloor motion effect, kinematic rupture of the earthquake. We investigate how tsunami-genic factors will influence the tsunami size and tsunami behavior in the deep ocean and along the coastline. Prior to the investigation, we need a realistic reference finite fault model, so we download the 3 USGS finite fault model, that is version 3, version 4, and version 5. We present the 3 finite fault model in the top row, and then we conducted tsunami modeling and compare the result with the data observation. We found that USGS Firefall model version 3 can explain most of the dot waveform, while version 4 and version 5 can only explain half of the waveform. Therefore, we choose the USGS Firefall model version 3 as our reference Firefall model. Based on the Firefall model version 3, we refine the co-seismic tsunami source by considering the uniform Earth model as model 1, layered Earth model as model 2, horizontal seafloor motion effect model as model 3, and the kinematic model as model 4. We built the model in a progressive way. Each subsequent model is an enhancement of the previous one by adding new components. There is a huge difference among the models. The layered Earth model, model 2, relative to the uniform Earth model, model 1, only increased slightly by 2%. Horizontal seafloor motion model, model 3, relative to the layered Earth model, model 2, increased slightly by 32%. That means the horizontal seafloor motion effect contributes significantly to the co-seismic tsunami source in the 2025 Kamchatka earthquake and the tsunami event. Model 4 is the dynamic version of Model 3. The only difference is that Model 4 considers the earthquake kinematic rupture. You can say the top row is crustal deformation, and the bottom row is tsunami displacement. When compared to the crustal deformation at the end of the rupture, the difference between Model 3 and Model 4 is that the area of the tsunami uplift is wider, and the area of large tsunami displacement is lateral. In the following slide, we will present the tsunami behavior and the tsunami size in the deep ocean and along the coastline. In the deep ocean, the tsunami amplitude and energy amplified in the rupture direction but decrease in the opposite direction. To clarify the difference, we simply use red square to highlight the result of the dot station located opposite to the rupture direction. Along the coastline, tsunami head changes over 5% in over 50% of the coastal area for the 2024 Kamchatka earthquake and tsunami event. In conclusion, we find the layered Earth model slightly increased the vertical displacement but greatly increased the horizontal displacement, eventually raising effectively tsunami uplift. Second, the kinematic ruptures amplify the tsunami energy along rupture but reduce it opposite. Third, nearshore impacts show more than 5% changes in over 50% of the coastal area, strengthening the need for accurate co-seismic tsunami source. Thank you very much for your attention and time.
You. Are you there? Looks like not. Okay, thank you very much. Okay, next speaker is Dr. Hiroaki Tsushima-san. Real-time tsunami source inversion using ocean bottom pressure record within the source regions, incorporating tsunami, seafloor deformation, and long period seismic waves.
Okay, thank you, Chair. My name is Hiroaki Tsushima from the Meteorological Research Institute of JMA. I am working to improve tsunami early warning using seafloor pressure records. Today, I want to talk about the new method of real-time tsunami prediction using seafloor pressure records, which include long-period seismic waves. After the 2011 Tohoku earthquake, dense seafloor network were deployed around Japan, and these networks include the ocean bottom pressure gauges, which can detect tsunamis before the actual tsunami reaches the coast. And therefore, these observation data are useful for early update of the tsunami early warning. Actually, numerous types of the method were proposed, such as the source inversion technique, data simulation technique, and so on. And most of the methods assume that pressure records contain only tsunami signals. However, the actual pressure records include not only tsunami, but also other phenomena phenomena such as acoustic wave, seafloor deformation, and reaction force from the water column. Today, my talk is focusing on reaction force or dynamic effect. This effect is rarely used in the tsunami prediction studies. Okay, this dynamic effect is due to the vertical acceleration of the seafloor. For example, we consider the situation that seafloor moves upward, the seafloor seawater with an acceleration. Under such situation, inertial force acts downward on the water column and which generate a downward force on the sea floor. This is a reaction force. So this dynamic effect is active when the seafloor moves with an acceleration. So, for example, this dynamic effect is active during the tsunami generation process or a seismic wave propagation process. And here is simulated pressure records along the source region. And you can see the huge pressure variation immediately after the earthquake. This is a dynamic effect. So the amplitude is much larger than the seafloor deformation or tsunami. And in the previous tsunami studies, this dynamic effect was regarded as noise for the real-time tsunami prediction. However, recent studies demonstrated that dynamic effect can be used as a signal for the tsunami source estimation. This is because the dynamic effect is related to the tsunami generation process, as I explained before. So, if we can extract the source information from the observed dynamic effect in real time, we can improve the accuracy of the tsunami source estimation and real-time tsunami prediction. So, we incorporate the dynamic effect into the real-time tsunami prediction by combining two existing methods. One is T-fish, and the other is Kubota's method. T-fish is a real-time tsunami prediction method that is based on the real-time source inversion. And this method is already used in the operational tsunami warning system in JMA. However, this method does not include dynamic effect. On the other hand, Kubota's method can incorporate the dynamic effect for the tsunami source inversion. But this method is not customized for real-time analysis. So we combined these two methods by taking advantage of each method. Okay, let me explain the Kubota's method firstly. Here we consider the situation that the seafloor deformation UZ generate tsunami. Under such situation, the observed ocean bottom pressure change can be expressed by the summation of tsunami, permanent deformation, and dynamic effect. So, as you can see, all the components are represented by using the UZ, a seafloor deformation. This is a key point. On the other hand, we can represent the seafloor deformation UZ by the linear combination of the two functions, large UZ and tau k. Large UZ indicates the unit source distribution, and tau k is the source time function of the unit source. So by substituting equation 2 into the equation 1, we can obtain this equation 3. This observation equation connects the observed pressure change and source distribution. So by solving this equation in the least square sense, we can estimate tsunami source distribution from the observed pressure change. So in this equation, G dynamic is important. This Green's function links between the observed dynamic effect and tsunami source information. Okay, this is a detail of the G dynamic. As you can see, This Green's function is sensitive to the seafloor acceleration at the OPP location, I mean here. So due to this sensitivity kernel, we can extract the seafloor deformation information from the observed dynamic effect. This is a Kubota's method, and based on this formulation, we revised the Green's function of T-fish. We distributed unit tsunami source distribution into the potential tsunami source area shown by blue color on the left map. And source time function of the unit source was represented by the ramp function, like this. So by using these two parameters and simulation called juggles, we can compute the Green's function for tsunami and seafloor deformation. This procedure is totally same as the original T-fish. In addition to that, we apply the Kubota's method. Specifically, we calculate second derivative of time of this ramp function. We can obtain this function, and we substitute it into this equation. We can obtain the Green's function of the dynamic effect, G dynamic. On the other hand, when we perform the tsunami source inversion, we put a multiple source time function in the time direction, like this, in order to represent the complex time history of tsunami generation process in the inversion analysis. Okay, in order to check the performance of the proposed method, we conducted synthetic tests. Firstly, we assume the magnitude 9 earthquake at the location of Tohoku region, and then we calculate the propagation of the seismic wave and tsunami by the numerical simulation technique. And the resulting pressure waveforms are regarded as observation data. And such kind of synthetic observation data include not only hydrostatic pressure change, but also the dynamic effect. And our synthetic tests were performed on two cases. One is the purpose of the case one is to verify the performance of the conventional T-fish. And the second test was conducted in order to check the performance of the proposed method. Okay, let me show the result of the case one. This figure shows the estimated source distribution, and the red color indicates the elevation, and the blue color indicates the subsidence. And the parameter TA indicates the time of forecast execution. Okay, look at the result just after the earthquake. Immediately after the earthquake, sea surface and sea floor moves simultaneously, so no pressure change is observed inside the source area. So immediately at that timing, estimated source extent was too small compared to the correct one. And then, as time passes, tsunami propagate outside the source region, and the tsunami can be observed at the pressure sensors outside the source region, and seafloor pressure change due to the seafloor deformation is observed inside the source region. Due to this observation, we can obtain the accurate source distribution like this. For that case, 10 minutes observation is sufficient to obtain the accurate tsunami source model. And then let me show the result of the case one, in which we apply the new method. So different from the previous result, we can estimate the accurate source extent. However, the source amplitude is slightly large, and as time passes, source distribution became close to the correct one. So in order to understand why our new method obtained the accurate source model just after the earthquake, we compared tsunami waveforms, pressure waveforms, which were used in the inversion. Here is a waveform comparison at the stations, which is located inside the source region. So leftmost panel shows the comparison for all the pressure component, And the three panels to the right indicates the pressure waveform for each component. I mean the tsunami, seafloor deformation, and dynamic effect. So this is a result when we use the 3 minutes observation. So as you can see, pressure change due to the tsunami and seafloor deformation cancelled. So the resulting hydrostatic pressure change is little. On the other hand, dynamic effect is clearly observed at this timing. So our accurate source extent was due to the observation of dynamic effect. And this is a result when we use the 10 minutes observation. At this timing, hydrostatic pressure change is well observed, which improves the separation of each component. Okay, finally, let me show the prediction results at the virtual station, which is located near the source coastal stations. So bottom figure shows the comparison between the observation and prediction. Black is observation and red is prediction. So immediately after the earthquake, predicted height is substantially large, but slightly overestimation. So although there is a room for improvement, such kind of overestimation, our new method can enhance prediction capability soon after the earthquake. Okay, here is a summary. So time is already over. I stop my talk. Thank you for your kind attention.
Thank you very much. Nice talk. Do you have any questions?
Thank you. It's a very good presentation.
Thank you.
I'd like to see the slide which has shown the temporal basis function of the seafloor deformation. Would you kindly explain that the time dependence? I find the sine function involved in it. Would you kindly please explain that part, that temporal basis function of the seafloor deformation? This is first one. And second is, so far as I know, there is an active generation and passive generation concept in tsunami generation. So has it anything to do with the passive generation case, what you have studied here?
So for the first question, you mean the whether or not I perform the multiple time immersion? Okay. Yes, we did the multiple time function. So the total duration is 2 minutes. And each time length is 10 seconds.
Okay. Okay.
Okay. Sorry, please repeat second question.
The second question is really related to the active generation and passive generation concept of tsunami. Active generation and passive generation concept of tsunami, where the bottom deformation is taken into the surface and it is called the passive case. So has it anything to do with that difference? Because in active generation case, the bottom disturbance is there, but in passive case, it is taken at the surface of the water. So there is a difference in the calculation, slight difference takes place. Has it anything to do with your application of the pressure change, dynamic pressure change that you, hydrostatic pressure change that you were mentioning?
You mean whether or not I consider the, for example, the depth filter or no? Yeah. When we produce the Green's function, we apply the depth filter to obtain the sea surface displacement from the seafloor deformation. Okay.
Okay. Thank you.
Thank you.
Okay.
Thank you. Very good question. But of course, it depends on the parameter of the source dynamic. So in this case, okay. For example, this is just above the source region. This is 130. On the other hand, this is a tsunami amplitude. So about the 5 times difference. Okay.
5 times.
Dynamic pressure is higher.
Yeah, 5 times higher. Yeah, thank you.
Okay, thank you.
Yeah, just one comment. Thank you for the presentation. Just to clarify, maybe that at the concept level, I don't believe that the idea is new. It goes back to 1982 from Yamamoto. So the concept of the use actually of the dynamic pressure as where you can extract the properties of the source, right? So this is one thing. My question is about if you're including the compressibility of the water, if you include the elasticity, and if you also consider different layers of earth curvature, how far did you go with this?
So now I consider the incompressibility of the seawater. So our synthetic observation includes the, just a moment. Acoustic, you mean the acoustic wave? Yeah. So our synthetic observation includes the acoustic wave, but we remove it by the low pass filter. Now.
Why do you remove it?
Because now we didn't model the acoustic wave in our observation equation. So I think it's future work to incorporate the acoustic wave for the tsunami source immersion.
It would also, all the waves that are traveling from the source, from the dynamic part,
Yeah.
carry information about the source. So it makes sense to actually look into the acoustics. Thank you.
Thank you.
Thank you.
Thank you for good discussion.
Thank you.
The next speaker is Dr. Bill Fry, and he is online, right? And he has a video, I guess. Guardian.
Yes,
Good
morning, everyone. My name is Siddharth Krishnamurthy, and I work at the NASA Jet Propulsion Laboratory in Pasadena, California, in the Space Weather and Ionospheric Remote Sensing Group. First of all, I want to apologize for not being present there due to the government shutdown. I'm very thankful that you're here to listen to this talk. I want to talk to you about what I think is a very novel way of detecting tsunamis, and what I think should be an augmentation to existing tsunami warning systems, which includes the ocean-based buoy system. This technique is called Guardian. Guardian stands for GNSS-based Upper Atmospheric Real-Time Disaster Information and Alert Network. And we've been developing this for the last few years at JPL. And I will go ahead and describe what this is, and I hope you will come to agree that this is a revolutionary and novel way of enhancing tsunami warning times. So here's an outline of my talk. I will first introduce to you how tsunamis are detected using GNSS-based remote sensing. We have this new augmentation to our system, which is called Guardian Scout, which is helping integrate machine learning into identifying tsunami signatures in real time. Talk a little bit about that. I'll share with you some very interesting results that came out of the recent Kamchatka event that I'm sure is being talked about a lot at this conference. And lastly, I'll motivate some conclusions in future work. So GNSS-based remote sensing for tsunamis is based in the idea that things that happen on Earth and also in space affect the ionosphere. And so if you have natural hazards such as earthquake, volcanic eruptions, or tsunamis, they launch these atmospheric waves that travel up to the ionosphere and then perturb the ionosphere. If you happen to have a navigation satellite communicating with a receiver where the line of sight passes through that area, you can actually be very sensitive to these perturbations. What you measure typically is something called TEC, total electron content, which is the electron density integrated along this line joining the satellite and the receiver. And that's what you see in this movie down here in the aftermath of the Tohoku Oki earthquake and tsunami, you can see the appearance of these waves in the TEC plots. And this was done with hundreds of stations in Japan. So that's why the density is really, really high. But what we actually use is the global differential GPS network. It's a global network of 200 plus sites. And I think the key thing here is that they all transmit data in near real time, which is what makes it useful for a tsunami warning system. So for instance, this movie was made in post-processing mode, and so like well after the tsunami had happened, whereas like we can look at this in near real time. So as we go forward, the thing I want to point out is that our objective here is to use this GNSS derived TEC data to augment natural hazard warning systems. So GNSS-based remote sensing for tsunamis relies on the geometry of the problem. Because GNSS satellites are so far away, any station can look up to about 1,200 kilometers away in any direction from where it's installed. What that means is that you don't have to put this in salt